everyone, or good afternoon. I'm going to talk about reasoning in natural language. As you can see, I have two titles here, two hats that I'm wearing. I'm going to talk almost only about work done with my group in University of Pennsylvania. Maybe one or two slides will address something that we're doing at Amazon. With this, let me start by saying what we all know, and that is that AI is in the news. I mean, a lot of stuff is happening over the last few years, and in fact, the slides here is already all news. What we have today are news about, have we solved it all? Is it AGI? And we know about ChatGPT making the news, the fact that Microsoft is building on top of it, the fact that Google is also involved in this AI competition, and only a couple of weeks ago we heard that Amazon also has a large activity in this space. But at the same time, we hear about a lot of problems. I mean, problems that mostly have to do at this point with hallucination, truthfulness, and so on. So we've seen, news that were generated that basically mention names of people in context that they shouldn't be mentioning. And as a result of this and some issues of privacy, we've also seen regulators getting involved. Italy banned ChatGPT or OpenAI models for about a month. The EU regulators are also in business and are trying to question what needs to be done. And even though the OpenAI ban in Italy is gone, it's completely clear that the regulators are going to be involved in this to the extent they can, and there are many interesting issues here. So where are we here in this game? So of course, everyone is very excited about ChatGPT and similar technologies, and there is a lot to be excited about. And I think that if we are going to make the right decisions, indeed, this technology will allow us to develop an advanced and very useful assistive technologies. And this is really how I'd like to think about it, as the goal is to develop assistive technologies rather than any other kind of names that you've heard about in the news. And in the course of this process over the last couple of years, we've already learned a few important things about what is hard and what is easy to do. And I think that we still need to be very, very careful to not misinterpret this technology. I mean, we have to be aware of the problems it could cause, and we have to be aware of the limitations, and we should not think as if we solved it all, because we haven't, and we are in many respects very far from doing so. So my goal in the first part of this talk is actually to provide you with some perspective, my own perspective on where we are and where should we go to. And then in the rest of the talk, I'm going to talk a little bit about some steps that are done in my group at Penn to address this. So to start, I want to go back maybe 55 years ago to a research program that Terry Winograd did as a PhD student at MIT. He developed a program called Shrewdlaw that actually was very, very excited in its time. I mean, really a conversational system, a computer program that was a conversational system that managed to maintain a conversation with users about real world things, about, in this case, the blocks world. And some people thought that problem solved, even though I'm sure he knew how far we are from solving it. And indeed, the conversation then was held with respect to a very, very small world. It didn't have any ambiguities because of its size. There was single option for all decisions and problem solving and co-reference and so on. Nevertheless, it was quite impressive at that time. So today we have much, much better conversational capabilities. ChatGPT and other models can keep a conversation. And you probably all heard about, the conversation that one of the tech journalists at New York Times held with ChatGPT. That was, in some respects a little bit scary, but definitely very, very fluent. So I'm zooming in here to show you some of the text that was generated by the model. Very nice from the perspective of being fluent. This is the first lesson that we've learned from this technology. We didn't know this ahead of time, and we learned that being linguistically coherent is much easier than we thought. A deep model trained on trillions of tokens to predict the next word can actually generate coherent text. What's in the text is another issue, but that's an important lesson that we learn. Going back to the communication with computers, I'm fast forwarding 50 years to a project that we ran in Illinois and Penn that was called Communication with Computer, and kind of similar to what Terry Winograd did. We also tried to converse about some world, and in this case we played with Minecraft, and we had an architect that defined goals and a builder that was supposed to converse about this goal, clarify them, and execute. You can see here on the right an example of a conversation with such a model. So what is the difference between Terry's kind of limited world and what we tried to do with Minecraft, which was almost open domain? We tried to build, for example, this giraffe. And the key difference was that at that time, we could actually use machine learning to train models to follow instructions. And the type of instructions that we try to train are things like this. I mean, as a way to train models, we placed blocks on a table. We actually named them to simplify the reference problem. So some of them were, McDonald's, Toyota, AWS, and so on. And the type of instructions that we train the models on are, I need to move UPS from the left side of the board just below Starbucks, leaving a small gap. However, as we were collecting data, we also saw that humans wrote the following instruction. Imagine that this is a chessboard. Place the UPS in H2 and McDonald in G6. Can you follow these instructions? I'm sure you can, and I'm sure that every 6 years old, if with the appropriate explanation, if they don't know chess already, can follow this instruction. But what is needed for us to be able to induce programs that can do this? So just a small detour. Why do I talk about following instructions? Really, following instruction is the key leap made with this new technology. Even today, if you want to solve one specific problem, a specific type of information extraction, a summarization of type XYZ, specific type of question answering, it's really better to train a small model for this specific task. The major leap that we've seen with the new technology of language models is that now we can define tasks on the fly by instructing the model to perform a task that it was not aware of or it was not defined before. We can summarize for elementary school kids, or we can extract something and list it alphabetically, or we can do many, many other things by generating instructions on the fly. So following instruction is really interesting. However, it's completely clear that models trained to predict the next token have limitations, and some instructions they will not be able to follow correctly, even though they could get lucky sometimes. So one perspective that I have on this is that, as human beings, we were trained all our life to equate being linguistically coherent with being smart. And we project this on our current conversational models. But this isn't the case. Much, much easier to be linguistically coherent than do many things that we expect models to do, but they cannot. And I'm going to give you a few examples. I'm going to run through many examples. I'm sure many of you have played with this and know. Here is one example of spatial reasoning. where basically I'm providing some instructions that describe some spatial configuration. I'm zooming in so you can read this better. And if you think about this, the way you would address it is you kind of plot it this way. And it turns out that sometimes a model can do it. GPT-4 can solve this correctly. But really it solves it because the instructions are very clear, and just being token biased, sort of biased to predict the next token, when you see something is on the left of A is on the right of B is on the left of C, provides the ability to solve this. But if you do this systematically and you try to generate data sets that challenge the models with these kind of problems, you see that the models actually are not that good. They solve a relatively small percentage of these challenges. Moving on to other problems of reasoning about sets, for example. And again, I'm going to zoom in on one problem here. Every person in the US is taller than my sister. So I wonder if every person in Alabama is taller than my sister. And you know, the model is giving an answer. And the answer is very verbose and it's fluent, but it makes no sense at all. The answer is simply yes. Logically, you don't need to deal with heights and locations and averages and so on. It's simply yes. It's a simple logical question. But the model being very verbose, but cannot identify that there is a simple logical structure here. You can go to quantitative reasoning, and I'm not going to spend a lot of time on this and see that sometimes models make a lot of mistakes. And I'm going to dwell a little bit more on the scheduling problem here. The problem here is I'm a scheduler and I need to schedule a 30-minute meeting for Tom, John, and Mary. And I'm going to give you some constraints on their time. And the question is, when should I set up the meeting? And again, you see that the model is very verbose and describes a lot of things. But the bottom line is that the only time that works for everyone is Monday morning. Each one of you will identify this in a few seconds. And the response from the model is mostly nonsense. And it's even possible to continue the conversation with it. The conversation is going to be interesting and coherent, but wrong. Because models that are only capable of sequential reasoning cannot get it in general. So the models that we have today are basically autoregressive models, as I show here on the top left. Essentially, they are feed-forward models. I mean, what they produce goes back to the input, and then they feed-forward it. And they cannot do backtracking that is required in some of these problems. Moreover, these models are trained to predict single tokens. And what I show here in the bottom right is kind of two ways of training these models, kind of in this case, an encoder model where the context is two-sided. On the right side is a decoder model when we predict the next token in the sequence. And by the way, this way of supervising models is really the key reason for the original excitements from language models. The hope that we can get around old machine learning, where we had to annotate a lot of data for supervised machine learning. And the idea was that now it's self-training. You take text, you drop a word, and you try to predict it. And even though this is not a new idea, it existed in NLP for the last 30 years or so, with these powerful models, it's very, very powerful. However, this excitement is not justified anymore because today models are not being trained this way. I mean, all the very large models use actually huge amounts of supervision and reinforcement learning from human feedback. This is very costly, in fact, more costly than earlier supervision protocols, but they are needed in order to facilitate and equip them with the capabilities that we see today with the model. So the example that I've given so far is not a random collections. There are multiple directions we can think about that expose the limitations of these language models. And I'm focusing here on one of the examples the problem of maintaining a large intermediate representation and reasoning over it, because these kind of problems often require us to do some backtracking or planning. I'm not saying that we cannot address these problems. What I'm saying is that we cannot expect language models as is to do it for us, and we need to augment them in various ways in order to solve such problems. And I'm giving here, a small collection of types of problems that in principle, not on one or two problems, models cannot solve. Problems that have to do with aggregation over intermediate representations, quantitative reasoning, dealing with spatial data types like space and time, and many other classes of problems that have to do with subjective facts, and of course, with truth. Models cannot tell the difference between truth and things that seem true. I'm giving here multiple example. The one example here on the left is a list of, or a request to generate a list of South Indian restaurants in Philadelphia, and all of these look like South Indian restaurants in Philadelphia. The only problem is that most of them do not exist. But it looks like it. So I'm going to finish with one example that I find very interesting and I like, and hopefully those of you that understand American football will appreciate. This is a story about a football game between the Eagles and another team. And I can look at this story and ask a few questions. The first question I could ask is, how many touchdowns did the Eagles score in the first quarter? And those of you that managed to read this will easily answer this question. I'm highlighting the reason here, and the answer is indeed 2. The text just says it verbatim. How many field goals did Washington score? And that's a little bit harder because you really need to know the rules of the game. And you know that the score is 49, and it's a little bit subtle. Most people would say that understand the game would say immediately 3, but really there are multiple ways to get to 9. And the reason 3 is the right answer is because we know that at least 2 field goals were scored. And if at least 2 field goals were scored, then 3 is the only options. And finally, I'm going to ask you, how many field goals did the Eagles score? And you notice that the text doesn't mention any field goals scored by the Eagles, even though, again, if you understand the game, you'll immediately see that they moved from 14 to 17, and the answer must be 1. Now, you can pose this question to ChatGPT or GPT-4, and you will see that the model indeed says the given news story doesn't mention any field goals scored by the Eagles, and it doesn't know how to answer it. And this is not a coincidence, because the reason I'm giving this story is because I want to, one of the key issues that we have to think about as we think about reasoning with models or in general is that really the world has a symbolic structure. People often, but not always, find this symbolic structure and use it in order to reason consistently. Sometimes they don't need to because it's simple enough. But language models as is cannot find this symbolic structure. Sometimes just using token bias to predict the most likely next token, given the huge context that you have, produces the same response as if they found it. And this leads us to the second lesson that we've learned. We've learned that often, maybe more often than we thought, token bias is sufficient and it's consistent with the reasoned conclusions. So some people can think about it as what Daniel Kahneman called think fast versus think slow. So this is kind of the think fast, and it's sufficient sometimes to give consistent results to the think slow. However, this is not what we want. Our expectations from our computers is that they will find this structure and be consistent. Right? Imagine that your calculator gives you correct answers only 70% of the time. You will never use it. So how do we equip models with this ability to sometimes, as when needed, to actually identify the symbolic structure and reason about it? And that leads me to the rest of the talk. And I want to talk about these three topics. First of all, I want to argue that LLMs cannot do it alone. We need to augment them with the ability to plan and backtrack, to interact with external worlds, ground themselves in those, and reason about it. We need to be able to learn to reason, figure out how to identify the structure of the problems, identify the variables, if you want, one needs to reason about, or the program needs to reason about. And this, I think, will require new supervision protocols beyond what we are doing today. And I want to finish with an application that I think is really important, and its importance is even strengthened by these new technologies. So what do I mean when I said that language models cannot do it alone? So I'm going to ask you a question that, in fact, ChatGPT today knows how to answer, because it saw this question and answer many, many times already in its data. But I bet most of you do not know the answer for this. In Yokneam, in what months of the year is the longest day? So while I think that you probably don't know the answer, you all have a plan for how to figure out the answer. And you know somehow, not sure how, that all you need is to figure out where is Yokneam. And in fact, not exactly where it is, but rather which hemisphere is it? Is it in the northern hemisphere or the southern hemisphere? And once you know this, you know the answer. Now, for some other places like New York or Boston or Melbourne, you don't even need to do this, because this answer is written verbatim in many, many places. But in the general case, you need to develop a plan. And the idea of developing a plan is really important in many, many other situations. I could ask you, are we going to make it to the movie? And this is really a very simple temporal reasoning problem. I need to know what is the time now, when does the movie start? And Google Maps is going to help me to figure out how long it's going to take me to get to the movie. But I can make it more complicated. Will we make it to dinner before the movie? And now the temporal reasoning is very similar, only that I also need to estimate the duration of dinner. And this will depend on whether I'm going to go to a fancy Japanese dinner or Chipotle. And there are a few other considerations I have to take into account, or my model needs to take into account if it wants to assist me here. What about parking? It's not mentioned in the body of the question, but we all know that this could be an issue if I'm driving there. And what if I try to make a reservation and didn't get it, and I have to backtrack and change something? So I have to be able to plan. And of course, I can make this problem a lot more complicated by adding a few other things. The temporal reasoning part is essentially the same. Is the end time of the game or the dinner before the start time of the movie? But the bottom line is that I need to identify this compositionality, and models sometimes can do this today. But the key is that there is a planning process that includes backtracking and often also calling external models. And this ability to call external model and reason about when and how to use it is really important. Here's another example. I could show you this picture and ask you when and where. And all of you can think a little bit about it. Maybe you know it off the top of your head. Maybe you'll have to do some search in order to figure it out and ask some questions. But you will all be able to tell me approximately what time period this picture was taken in, and probably also the general location it was taken in. And an even easier problem, at least to the American audience, would be the picture that I show here. If you've read the news over the last few years, you'll be able to place this picture at least in a time period and definitely in a location. And again, this is something that most people may not be able to do off the top of their head, but they will be able to consult some resources. And I'm mentioning this, I mean, this is a paper where we built a data set to support this kind of reasoning and to motivate high-level vision language models that actually have to conduct open-ended reasoning with access to the world. And this idea of access to the world, I think, is one of the key issues about facilitating what we want to do with language models. So this is the only mention, as I said, to work we are doing in AWS AI Labs. This is something that we've done about a year ago, long before ChatGPT was out and long before all these ideas, good ideas of using plugins and so came up. And the idea was, we call this dialogue to API. And the idea is basically that language models should facilitate the ability to converse with any software system. Could be my PowerPoint, could be a scheduling program, could be AWS APIs, or any of your favorite productivity tools that you like to use. And this is really where the disruptive ability of these models is going to be, I think. So with that, let me move to the next part, where I want to talk about learning to reason, and basically give some ideas on the need and the how to identify the structure of the problems. Really, the question is, what are the variables that I want the program to reason about? And I'm going to start with another problem that today ChatGPT can solve. Again, just because it has seen so many examples of this in the RLHF process or others. I'm sure many of you know who this guy is. This is, if you don't, this is Aristotle, the guy that founded syllogism, basically reasoning, a method by which non-information can be used to prove a point. And I could ask you whether Aristotle have a laptop. And I'm sure many of you, I cannot see you here, many of you are laughing now because this is a trivial question. Of course he didn't. By the way, a couple of years ago when I tried this last, when I popularized this question, if you were searching for Google or on Google for this, the answer would have been yes, because there is a book that is titled Aristotle's Laptop. So if there is a book, then definitely had a laptop. But really the bottom line is for us is, what are the variables that we have to reason about in order to laugh about this question? The variables or the components of this are not given to us. But nevertheless, I'm sure that all of you would identify something like, I need to know approximately when did Aristotle die. I need to know approximately when was the laptop invented. And I need to know which one happened first. But the real question is how to do it, how to determine these strategies, these components on the fly, and of course, how to supervise for these sparse events. So if you want a few other instances of these kind of questions, there is a data collection that we've put together a couple of years ago, a data set that is called Strategy QA, that models are beginning to be better and better at solving, largely because we kind of engineer them to death, not because of developing strategies in most cases. But that aside, let's think a little bit about what does it take to be able to decompose problems to these components. So I'd argue that really reasoning can be thought of as the process that is supposed to provide reasons. Reasoning is really about providing reasons. So let's look at this example. Can Cyril Ramaphosa become a Secretary General of NATO? So if I present this question to a geopolitical expert, they would immediately say no. If on the other hand, I would present it to an educated adult reasoner, they would say probably, I don't know. Until I tell them, well, she is the president of South Africa and NATO only contains North Atlantic countries. So an educated reasoner would immediately say, okay, no. Notice what I've done here is I gave them the variables, or really the propositions, because they have truth values that form the premise. basically, I provided them with the background knowledge, and now they are equipped with the ability to know what to reason about and what to put together as a way to generate the know. Now, I could ask the same question to a 6-year-old that would probably say, I don't care. And in that case, I would have to give them a lot more details, a few more variables, in order for them to be able to reason about it. And the same answer, hopefully, is going to be produced. The answer is no. So weaker reasoners need stronger reasons or more variables in their background knowledge, but the story is about the same thing. I mean, we need to be able to identify these reasons. We need to be able to decompose. And the key questions are really, how do we decompose? And of course, how do we know which level is enough? I'm going to address the first question, which is, how do we decompose? Really, I'm thinking about the decomposition as a way to explain the reasons, or to find the necessary variables or propositions that support the reasoning process. Why isn't it trivial? It's not trivial because it's not written in most cases explicitly in the text. I mean, it doesn't often happen that you will see a sentence in the same source, in the same document. The Albany in New York is more crowded than the Albany in Georgia. The Albany in New York has more people and less space. Because once people read the statement in red, they actually know the statement in green and vice versa. So no author is going to write both of them. But this is actually the solution to identifying variables. While language models cannot easily pick up such equivalence with the way we train them today, we can change the way we train them. We can use what I call incidental supervision signals as a way to train model to identify these variables. And let me give you an example of using these incidental supervision signals using comparable text. So let's assume that you have a collection of comparable news articles that describe the same thing, the same event, for example. Document source A describes it from one angle and source B describes it from another. Then I can use this if I know that they actually are grounded in the same event or in the same story to supervise one from another. Let me give you here an example. So let's focus on the third example here. If I have one source that talks about gophers and says that gophers hide in holes and tunnels, and a second source talking about gophers says that gophers are capable of digging holes much larger than themselves, now I know that these two are related, and the ability to hide in holes and tunnels probably is related to being capable of digging holes much larger than themselves. So this idea of generating this kind of supervision signals triggers a way to train models. I can try to train models by feeding them one of these statements and asking them to predict the other. And by doing that, I'm going to teach them these equivalences. So to accomplish this, I need to collect distance supervision signals from parallel news, train models, and develop a QA pipeline so that I'll be able to show that this actually helps me in answering this type of difficult questions that require these decompositions. Now, I'm not going to give you all the details here, but I would just say that we can do this. We can develop this extraction pipeline, and we did this in a paper that was presented a few months ago at EMNLP, and this pipeline resulted in about 2.6 million sentence pairs, sufficient to train a relatively large models. And once you train a large model with this, for example, you put as input into a T5-like model, Albany, New York is more crowded than the one in Georgia, and you want the model to predict that the Albany in New York has more people and less space. you can generate a model that we call decompose T5 that understands better how to decompose sentences into their core propositions. Of course, there are multiple research questions here. For example, we want to know, as a result of this training, whether this model is better than the standard T5 in reasoning. We want to be able to know whether it better supports downstream tasks like question answering. And the answer for these questions is yes. I'm not going to give the details again, but if you would like to get these details, you can consult this EMNLT paper. And I'm going to skip the rest of the details of this and talk about the last component that I wanted to discuss. And the last component has to do with applications. One of the key things that NLP researchers should do today, beyond kind of the core problems of that I just addressed, is thinking about applications. And there's no more important application, in my view, than thinking about navigating information pollution. And of course, the fact that we have these new powerful ways to generate information in an easy way just strengthens the importance of this. So I'm going to spend a couple of minutes talking about this problem. So of course, mis or disinformation is not a new phenomenon. I'm showing here a couple of books that you may be interested looking at. The book Active Measure actually provides a history of disinformation going back many decades ago. And on the other hand, the book The Perfect Weapon is a more current view of this. But anyway you want to think about it, this is something that existed all the time, only that the information revolution and now generative models have made it much easier to generate dis and misinformation and really impact more people in more areas of our life in a much easier way. So and of course, as we know, this imposes risks on the major institution of our society, and we want to be able to think more about it. I would argue, though, that factual information or lack of it is not really the core of the problem. The core of the problem is comes in two interrelated flavor. One of them is that there's a lot of information out there, and this information pertains to give us answers to questions. But it disregards the fact that there's no one answer that fits all. So the picture that I put on the right side, there are responses to the question of should we allow experiments in animals? And there are multiple perspectives of this. They depend on context, they depend on what animals, they depend on many things. And some people would answer yes and would argue this well, and some people would argue no and would argue this well. And if you ask yourself this question, it's important not to get an answer, but rather to be exposed to the perspectives that exist. So this is one flavor. And the second, of course, is the misleading, malicious mis and disinformation that comes from people that actually have an agenda, often hidden from the audience, but an agenda that generally attempts to cause chaos. So the research program that we've developed in this area over the last few years really thinks about it as providing readers with a proxy that is really an investigative journalist, because that's what we need today. We can't just read what we see there without kind of thinking about it and trying to qualify it. So the goal is to develop a computational model that supports navigating the polluted information world. And we've been thinking about it as consisting of three directions. One of them has to be developing perspectives with respect to claims and statements. The other one has to do with information provenance. That is a notion that extends kind of the notion of provenance from databases. And the third one is a direction that has to deal with identifying and qualifying sources, expertise, and trustworthiness. And I'm going to talk, and I have a research group in this, some of my students, and some papers that we've generated in this space over the last few years, and more is coming. And I'll have time only to talk about the first of these, perspectives. So what do I mean when I talk about perspective? So as I said, most of the information that we care about does not have a single correct answer. So I can ask a question like should animal have lawful rights? And people will give multiple answers with some support. So rather than providing a list of relevant articles, which today search engine provide us with, really driven by keyword match and previous searches, we should be able to develop an approach that is aware that there are many ways to respond to queries. We have to be able to understand the information needs, we have to understand all the relevant information that is available, and we have to be able to present it with clustered into multiple perspectives with evidence and support. And basically the computational process that we have developed for this, starting with a query, you want to be able to find all the relevant articles, cluster them, summarize them, and develop a concise perspective that will allow us to understand, what each cluster really stands for. And of course, all the relation between these, whether they oppose or support each other, whether they support the claim or oppose the claim. And this is basically an effort that requires us to develop multiple machine learning driven language understanding tasks. And the generative models that we have today will help improving the quality of this process. This effort is described or summarized in a recent paper in NACL 22, and you can go there and look at it, but we actually have a system that you can play with, a website that we developed that actually does this. Start with a claim, basically identify the different perspectives, provide summaries for each one of them and supporting evidence, and you can click on each one of them and get all the evidence or the key evidence that we identify as supporting this perspective. And hopefully more work is going to be done in this domain. And I'm happy to say that one of the up and coming search engines, Niva, has already adopted kind of this direction, and they've presented a multi-perspective AI, and their search engine kind of support the ability to think about perspectives. As I said, the research program consists of multiple other aspects of this navigating information pollution effort, including information provenance, expertise of sources, and trustworthiness, but I will not have time to discuss it, and I'm going to summarize with the following conclusion. So I talked about language models. Clearly, they are making big waves, and largely for the right reasons. However, we need to understand the limitations, we need to understand the advantages, and we need to figure out how to build on top of this new technology things that will actually be useful for us. And of course, how to restrain this technology. And I highlighted a few research efforts that I think are important, that have to do with planning, that determines what's relevant, what needs to be accessed externally to support decisions, how to think about learning to reason, how to think about understanding reason and explaining, how to extend the notion of supervision that we have today to more general supervision protocols. And as an application, I talked about the effort to navigate information pollution. And with that, I'm going to thank you and stop here. Okay, I'll try to go to the QA chat, but also feel free to drop me an email if you want to ask questions or discuss it in case I don't get to your question in the chat.